Hi, this is John, and this is my third video assignment of Fundamental Semiconductor Device 2. And today we're going to talk about MOSFET. And I'm here with better cameras. So, because I want to talk about MOSFET in this video with some little figures, so that's why I came with my new cameras. So, for the first, we're going to talk about the basic. We're going to talk about what is MOSFET and the structure of MOSFET. So I have a 3D structure, 3D figure of the MOSFET structure. As you can see, there's a top. At the top, there's a M plus polysilicon as we use as a gate. And usually we use this with a metal. And the second layer, there's an oxide that we use the silicon oxide as an oxide layer, and we use p-type silicon as a substrate in this figure. So I think I need another color. So if we cut this structure, this 3D structures with this direction, we just cut it, and we can see this cross section for the 2D figures like this. So as you can see, what I said before, there's a top, it's M plus polysilicon, but we use metal usually, so we call this part as M, and the second layer is the oxide part, so we called it as O. The third part is the substrate part, so we called it as S. So we usually call this structure, this layer structure, as a MOS structure. But I said it before, we're gonna talk about MOS cap today, so you might have a question about where the cap is come from. So as you can see, between these the metal part and the substrate part, there's a dielectric part, which is silicon oxide, right? And the metal and the substrate looks like a parallel plate, and the silicon oxide is located between those two plates, and it just looks like a capacitor, right? And it also behaves like a capacitor, so we call this device which behave like capacitor, is MOSFET. So for today's video, we're gonna talk about this MOSFET device. And for before they explain, and before we're gonna talk about this behavior, we have to know how to draw the energy band diagram of this MOSFET device, because it's the basic part to know about how it works or how it looks like and something like that. So I just draw these three energy band diagrams, which is isolated like this, and this, as you can see, this dot line is a Fermi level of metal, and the metal has a really close located Fermi level with conduction band. So I draw the metal part band diagram like this, and the middle part is oxide, the silicon oxide band diagram, and the third, for the substrate part, we use a p-type substrate part, so I draw a Fermi level and the valence band of substrate like this. It's really close to it, right? And there's a vacuum energy level with the blue lines. So we're gonna draw the whole MOS substrate, the MOS cap structure, energy band diagrams. For the first, we have to draw, let's ignore these three, we're gonna talk about it later. So for the first, we're gonna draw the Fermi level line very constantly, because we're gonna talk about we're gonna draw the band diagram in thermal equilibrium state. So we have to draw Fermi level really constant like this. And next, so the band gap, the energy band gap of those materials is a material property. So we have to draw their band gaps maintained. But the energy band gaps of metal doesn't change that much, so we're gonna use this as a standard. So we're gonna draw a metal band diagram like this. We're gonna maintain those energy gaps in this figure 2. And then we're gonna draw a p-type part like this. Also maintain those energy band gaps like this. So for the next, we have to draw. So we have 2 steps left. We have to draw an oxide part in here, and the full energy and the full vacuum energy part in here. First, we're gonna draw a oxide part by the energy bands of p-type goes up than the initial condition. We have to draw an oxide band like this, which has a slope. And also, I'm gonna draw a vacuum energy level with a blue pen. And also, in this material, the electron affinity is also their material property. So we're gonna draw. We also have to maintain those electric affinities also. So I'm gonna draw this the energy vacuum level like this. And we're gonna connect it really smoothly, and you can see the vacuum energy level looks like this. And for the last step, we're gonna draw the oxide part first, and we're gonna connect the p-type part smoothly like this. And this is the equilibrium state. This is the energy band diagram at the equilibrium state. And now we're going to talk about the behavior. I don't know if I said its property to say behavior, but we're going to talk about the accumulation and depletion and it's erased but inversion of the MOS cap, which use p-type as substrate. So for the first, when we when we put the negative bias at our MOS cap, MOS cap, and in here, which we call surface, which is the interface of the oxide part and the p-type part, we usually call this surface. And the surface, the hole, which is the majority carrier of these p-type semiconductor, is accumulated in this part because it's way closer, because its Fermi level and the valence level is way closer. So it is high hole carrier concentration. So we usually call this as accumulation. And for next, when we put plus bias on the gate, and then the p-type might be a negative, might be a negative bias, so its energy band gets way higher than the accumulation. And it just looks like this. And by the plus bias of gate, the accumulated hole, which is located in this surface, will push and move to a substrated part more, and this place might be depleted. So we can make a depletion region in this part. So that's why we call this process as a depletion. And for the last, when we put way more plus bias at the gate like this, and the p-type should be way more negatively, so the energy band will get more higher. And this is really interesting part. So in the depletion process, the whole moved to a substrated, so the whole moved to a body part, the substrated part. So we make a depletion region in here, but in the inversion part, there's a way higher positive bias. So there's only electron carriers will accumulate it in this part. So, and then if the electrons concentration is way higher than the doping concentration in body, which we call Na, if this happens, and if this happens, and this part, in this region, is not the p-type anymore, because there's way more electrons than the doping concentration. So it looks like an n-type. So as you can see, the charge of this part is changed. It's inversed. So this is why we call this process as an inversion. So I just explained these with the p-type substrate. So we have to talk about all this process with n-type. So we're gonna talk about it later. And I think I use so in my sentence so much. So I think I have to fix it. But anyways, this is my third videos, and this is it. And thanks for listening, and see you next time.